All right, started. Sorry about the initial delay. The computer was also on Thanksgiving break, it seems. All right. So in this class, we are going to still discuss a little bit about the op-amp design problem because this is very important for this class as well as for your exam number 3, which will be on next Monday. So this will be the last exam for this semester. There is no final exam. So this exam number 3, which is on next Monday, will be regarded as your final exam. So I have already uploaded some information about your exam that will be on next Monday, 1 week from now. The syllabus will be till today's lecture. So whatever is taught till today will be on the syllabus. Okay. And part of it will be self-study. So for example, on today's lecture, we're going to revisit the op-amp design problem a little bit. We're going to learn about basics of CMOS logic intro, but there are some self-study sections as well, which are on BJT basics and BJT AC and DC analysis. So I'll go over the BJT basics as well as AC and DC analysis briefly, but we'll not discuss them in detail. So I have uploaded 2 recordings from last year, from 2022, which you can go through. So both of these are 1-hour lectures. One of them is on BJT basics. The other one is on BJT AC and DC analysis. Now, what you'll see is that the analysis will be very similar to what you had for your MOSFETs. So for BJTs, only difference is that the BJT is a current-controlled current source, whereas your MOSFET was a voltage-controlled current source. You apply a gate voltage at the for the MOSFET and you get an output current. For a BJT, you apply a base current and you get a collector voltage, which is beta times that of the base current that you have. So we'll go over the BJT details in brief, but before we go there, I wanted to discuss a few things about your homework number 8 and the op-amp design problems, which I regard as important for your exam as well as for the overall learning on the topic. Okay. So please remember for the exam, you'll have to go through whatever is covered till today's lecture, and that includes the 2 pre-recorded lectures that I am uploading on BJTs. Okay. But whatever we'll study, let's say on Wednesday or Friday's lectures, that will not be part of your final exam. Okay. All right. Any questions? Yeah. Okay. So I think all of you are, some of you have already submitted the homework 8 solutions. But yeah, I just wanted to go over the solutions once more so that all the steps are very clear to you. So for example, the way we start this op-amp design problem is, again, if the load capacitance is not given, ask how much the load capacitance is in any kind of design problem. So you might be designing op-amps in future. For example, if you're doing internal TI or analog devices, it's one of the very basic fundamental circuits they start with. And they want to know whether you know how to design an op-amp or not. So the first most important step is that you should know what is the load capacitance. Because depending on the load capacitance, you'll select your Miller compensation capacitance that needs to be at least 0.22 times of your load cap. So if your load cap is 1 picofarad, you need to be at least 0.22 picofarad. So you might choose a value of the compensation capacitance to be 0.5 picofarads or 1 picofarad. So which will be more than 0.22 times your CL. And that will ensure that you have more than 60-degree phase margin that again is related to your stability. But as you increase your load capacitance, your slew rate will reduce. So you have to keep an eye on your slew rate, that if there is a specification that says your slew rate needs to be this much, so you have to have an upper limit on your compensation capacitance, because if you make it too large, your slew rate will become smaller and smaller. Similarly, the gain bandwidth product will become smaller and smaller if your compensation capacitance is too large. Now, of course, the way you solve this design problem, and again, by design problem, what we mean is that you need to find out the W/L ratios of each of these transistors in the circuit. You need to find the W/L ratios of all the transistors in the differential amplifier that you have as your first stage with a current meter load. and you need to find out what are the W/L ratios of this common source amplifier. The way you start that design is, of course, from the load cap value, you'll determine a value of your CC, and from your slew rate specifications, you'll fix a value of your I5. That's the current flowing through the tail current source through this transistor. So if you know the value of I5, which is the current through this transistor, you know what would be the value of the current flowing in each of these branches, which will ideally be half of the current flowing in the M5 transistor, right? So I5 will be twice that of I3. You can write your I3 as 2 times K over 2 times V over drive squared. And from there, you can just manipulate these mathematically formally to get to this form of the equation. Now, again, for VG3, that is how much voltage you can apply at the gate. In this case, you have to consider what is the minimum voltage that you can apply at the gate. And why is that? I have also posted an announcement on the Canvas page explaining that why you consider VG3 min when you are trying to find out the W/L ratio of M3 transistor or M4 transistor, and why would you consider or basically the for VG3 min, you'll actually consider the VIN1 max, the maximum value of the gate voltage that you can apply at the input. So the maximum range of ICMR that needs to be used when you're trying to find out the W/L ratio of M3, and the minimum range, the minimum value of the ICMR that needs to be used when you are trying to find out the W/L of the M5 transistor. Why is that? So you can, I'm assuming that you have already gone through the mathematical equations over here. If not, please go through the mathematical equations. But what I'm going to discuss now is that why would you even consider the VIN1 max when you are trying to find out the W/L ratio of the M3 transistor? That is not given in the handout, so that's why I want to discuss this in detail in the class. So let's just assume that your VIN1, that's the gate voltage for the transistor M1. Let's say that that gate voltage increases. Okay. So if this gate voltage increases, keep in mind that the current through the transistors will remain same because the current is determined by this tail current source. So you have a bias current and you're mirroring that bias current to this tail current source. So whatever current is flowing through the devices, that is already fixed. It does not depend on what is the gate voltage of your M1 or M2 transistor is, right? The current is determined by the tail current source. It is not determined by the VGS, or it will actually be also be determined by the VGS over here, but that's a secondary effect. That's not the cause, that's the effect. So we have to find out the cause and effect of each voltage and current in a circuit, right? If you want to understand that circuit correctly. So here what is happening is that you're biasing the differential amplifier using this tail current source, and that current is fixed because that is only determined by the W/L ratios of this transistor, the bias transistor, and the tail transistor. It is not determined by anything else. So if your current is fixed, as you're changing the gate voltage, as you're changing the DC voltage at the gate of the M1 and M2 transistor, what needs to happen is that the source potential also needs to change in terms of the DC voltage that you have, right? Because you know current is nothing but K over 2 times VGS minus VT whole squared in saturation. So if your current remains constant, so I'll just write that down, current or ID is equal to K over 2 times VGS minus VT whole squared. So if your current remains constant, and the current is constant because you have a constant current source at the tail. So if your current remains constant, your VT is already a constant, you know, the threshold voltage. So your VGS has to remain constant. So if your gate voltage, if the DC potential at the gate increases, the source potential also needs to increase by the same amount to make sure that you still have the same amount of current flow, right? So that's kind of like a negative feedback in the system that is inherently applied. You do not need to do anything else. You do not need to make sure that you do not need to connect a negative feedback to the input. It is inherent that because your current is fixed, your VGS has to be fixed. So if your gate voltage increases, your source potential also needs to increase, right? According to this equation. Of course, that this equation, if you want to be stricter, then what it means is that you have to consider the 1 plus lambda VDS term along with this particular equation, right? So in that case, you'll see that your VGS, if your VGS is fixed, your VDS also needs to be fixed because the entire current is fixed. So if your VDS is fixed, which means that the drop across the M1 transistor needs to be constant. So as your source potential increases, the drain potential also needs to increase. And if this drain potential increases, you see that this drain is connected to the gate of the M3 transistor. So the drain and the gate of the M3 transistors are connected together. So if this drain potential is increasing, the gate potential of the M3 transistor also increases. What that means is that for this PMOS, the M3 transistor, so let's just circle this. So for this M3 transistor, the VSG reduces, right? As the gate input increases, the VSG of the M3 transistor reduces. Now, at some point, it will be so low, the VSG of the M3 transistor will be so low that the transistor will not remain on or in saturation. So for example, this transistor, the VSG and VSD are equal because the drain and gate are connected together. So as you're saying that VSD reduces, it also means VSD keeps on reducing. So there is a risk that this M3 transistor will not be in the correct operating range as you keep on increasing the DC potential at the gate of the M1 transistor, and as you keep on making it higher and higher. So as this potential increases, there is a risk that this M3 transistor will go out of saturation. So that's why when you are designing this M3 transistor, you have to keep in mind that you also have to consider what is the potential at the gate of the M1 transistor. And that's why you consider V1 max when you are trying to design M3. Similarly, when you are trying to design M5, so I'll just remove all these writing over here. Okay, so when you are trying to design M5, you consider the V1 min. What is the minimum voltage that can be applied at the gate of the M1 transistor? Again, why is that? So as you are reducing the voltage at the gate of the M1 transistor, again, by the same logic, the source has to reduce because your current remains constant. Assuming that your current remains constant, the source voltage has to reduce. And if that source voltage reduces, which means that the drain voltage of this M5 transistor reduces. So for this M5 transistor, your VDS keeps on reducing. Now you know that the equation for saturation is that your VDS needs to be larger than V overdrive. And if the equation for saturation is not satisfied, then this M5 transistor will not work as a current source. So when you are trying to make sure that this M5 transistor is in saturation, that this transistor is in the correct operating region, and it is working as a current source, you need to consider what is the minimum value that can happen at the gate of this M1 transistor. So when you try to design M5, so that's in the next page, that when you're trying to design M5, you'll consider the VDS5, and in that VDS5, you'll consider the minimum value of your VIN1. So what is the minimum value that can be there at the gate of the M1 transistor? So that's why when you are considering designing the M5, you'll consider the minimum value of VIN1. When you are designing M3 or M4, you'll consider the maximum value of VIN1. So that's the intuition behind it, that why would you consider the minimum value for one and the maximum value for the other? Okay? All right. So yeah, I think that's about it. That's the most important thing I wanted to discuss here. And of course, you can find out once you have designed all the transistors, you can find out what is the GMs, what is the ROs of all the transistors, because you already have an idea about what is the GM for each transistors, because GM is nothing but K times V overdrive. If you know the V overdrives and you know the K values, you can find out what are the GMs. If you know what are the GM values and what are the RO values, and remember, RO is nothing but 1 upon lambda ID. So if you want to find out RO of one transistor, you need to find out what is the current, DC current flowing through that transistor, multiply that with lambda, and of course, the lambda value will be given. And if you take an inverse of that, you'll find out what is the RO. So for example, for RO2, it's basically 1 upon lambda 2 ID2. So for the M2 transistor, the value of lambda2 multiplied with the value of ID2, and taking an inverse of that will give you RO2. So you can find out what would be the overall gain, the total gain in this system. That would be the gain of the differential amplifier stage. So that's GM1 times RO2. So RO2 is the RO looking down at this output node in parallel with RO4. That is the RO looking up at this output node. So basically, again, what is the overall output impedance at this node? That's a parallel combination of the resistance you see looking up and the resistance that you see looking down. And that would be the GM times RO of this first stage. That multiplied with the GM times RO of the second stage, that will give you the overall gain. And that is the equation that we have listed over here. So this is the GM RO of the first stage multiplied with the GM RO of the second stage, that is giving you the total voltage gain. Also, if you want to measure the power consumption, that what is the overall power that you're consuming here, that's basically the currents that you are consuming in the I5 transistor, so basically the differential amplifier branch and the common source branch. In this case, because you are asked to find out the power consumption of the amplifier, you do not need to consider the power consumption in this branch. But if you consider it, just mention it. If this kind of a question comes in exam, just mention what you are considering, whether you are considering the bias current or the bias power as well in the overall power consumption, or whether you are not considering it. In general, most of the times, the power consumption in the bias network is not considered. You only consider the power consumption in the active network, the network that is giving you gain. So basically the differential amplifier and the common source stage after that. So the current being consumed in these two stages multiplied with the supply voltage. So for example, in this case, the supply is basically VDD, because on the other hand, you have a ground. So multiplying the total current with VDD will give you the power consumption, because power is voltage multiplied with current. Okay. But if you had a VSS, if you, let's say, had a -5 volt instead of this ground, then the power consumption would be the difference in voltages between VDD and VSS, because that's the, so what is the power consumption eventually? That if you have a resistor, the voltage difference across the two terminals of the resistor multiplied with the current that is flowing through the resistor is the power consumed by the resistor, right? So that's the same approach that you'll be applying over here as well. So if you have VDD here and VSS instead of ground, so VDD minus VSS multiplied with the total power consumption, that is I5 plus I7, will give you the power consumed in this network. So please go over the example. So it just uses the same concepts that we have studied till now. And then the homework problem is just a PMOS input version of the same thing. So again, for PMOS input cases, you just need to consider the absolute values to make sure that the transistors are in the correct operating region. Or basically, you can consider VSG instead of VGS, or you can consider VSD instead of VDS. So those are the only changes you need to make when you are considering a PMOS-based network. Question?
For example,
Exactly. So just go over the same logic that and that's why I discussed this in detail. That when you are considering, let's say the tail transistor, do you consider the max value of the input or the minimum value of the input? So just think about it when you are solving the homework problem, and it has to be related to the same concept that we just discussed. Okay, so great point.
That happens when we have favor current so what kind of same process before the mirror low or
for the differential amplifier. If you have a cascode transistor in between, that will make the calculation very complex. I do not want to go there in this undergraduate level class. So maybe in a graduate level class, yes, you may expect that, okay, there would be a cascode transistor in between, and the way you'll approach the problem will still be the same. It's just that the equations will not be exactly the same, but the approach will be very similar. Okay, if there is a cascode transistor in between, or if you see a different kind of load. But for an undergraduate class like this, please expect that, okay, if this kind of a question comes in exam, it should be very similar. As long as you understand the approach, as long as you understand the logic why you are doing these steps one after another, it should suffice for an undergraduate class. Yes. Diode connected load too. Yeah. So basically, this current meter load is diode connected in one end, and then it's a current source on the other end. You can consider it as a combination of the two, right? So yeah. All right. Any other questions? Yeah. If not, please go over the example, submit the homework solutions in time, because this homework will be very important for your final exam. All right. So I have also uploaded the self-study material over here, which is basically your BJT basics and BJT AC and DC analysis, along with a few examples on BJTs. So what you see is that the way you'll analyze BJTs, bipolar junction transistor, will be very similar to MOSFETs. Even though the behavior of the device is different, the way you will be using it in a circuit will be very similar. So just like you had common source, common gate, and common drain transistors for MOSFETs, or those configurations for MOSFETs, you'll have very similar configurations for BJTs as well. The biasing networks will also look very similar. The current meter will look very similar. The gain equations will be very similar. So you'll see, you can, if you go over those lectures, the pre-recorded lectures, you'll see that you can draw direct analogies between your MOSFET circuits and your BJT-based circuits. So that's why I'm putting this as a self-study, because by now, if you understand the MOSFET-based circuits well, you should be able to capture the basic concepts of BJTs very quickly. So what a BJT is ideally is, it's a combination of two diodes. So we already understood what a PN junction diode does. So let's say you have a P and an N side. So basically, let's say the diodes we have studied used to look like this, right? So now if you put two diodes back to back, so if you have a P followed by an N followed by a P once again. So let's see. Oh, okay. This was the diode configuration again, but the BJT configuration looks something like this. That you have a N-type region, then you have a P-type region, and you again have a N-type region. So this is an NPN BJT, and NPN BJTs are analogous to the NMOS transistors. Similarly, PNP BJTs are analogous to your PMOS transistors. So what NPN BJTs do is that you have a N plus region, you have a very small P plus region, and then you will again have a large N plus region. It's important that this middle region is very small. So this is called the collector, base, and emitter. So these are the name of these three terminals are collector, base, and emitter. Again, emitter is very similar to your source of a MOSFET. Emitter, the job of the emitter is to emit the charge carriers. They could be electrons, they could be holes. So if you have an NPN BJT, then you know that on the two sides you have the emitter and the collector. So of course, from the N side, the emitter, if you have an N-type emitter, it will be able to emit electrons, right? Electrons are N-type or negatively charged carriers. So again, emitters are very similar to source. Remember that in NMOS transistors, your source is a N plus region, or your source is basically an N-type material. Similarly, here your emitter is an N-type material. So this NPN BJT will be very similar to your NMOS transistors. Similarly, PNP BJT will be very similar to your PMOS transistors. Now, the way you basically bias the transistors will be very similar again for the BJT or the MOSFETs, but the details are provided in the document and also in the lectures that I have uploaded. So please go over the details, that how you can sort of. So the first lecture is about the device basics, that how do you design an NPN BJT or a PNP type BJT, and what are the properties of those devices. And you'll see that in the lecture, I'm providing direct analogies with the NMOS or PMOS transistors, so that it's easier for you to understand the working principle of these two devices. So basically what the equation, the most important equation that you'll be interested in is basically this, that for the transistor, if you're providing a base current. Now remember, for a NMOS, the difference was that there could not be any current going into the gate of a NMOS or a PMOS transistor, because at the gate you had an insulator. Here it's just a combination of PN junction diodes. So this is an NPN. So your emitter could be N plus, then your base, and then again your collector. So it's two PN junction diodes. So there is one PN junction diode over here, and then another PN junction diode over here. The idea is that you'll have one of those PN junction diodes forward biased and the other one reverse biased. So the one that is forward biased will try to push a lot of amount of current, right? Because in forward bias, you have a large amount of current for a diode. Remember that the diode characteristics look something like this. That if this is the diode current, and this is the voltage that is applied across the diode, in forward bias, when that voltage is positive and when the voltage is more than the threshold voltage, you'll have an exponential rise in the amount of current. So you'll try to make sure that one of the PN junctions is forward biased and the other PN junction will be reverse biased. Now, of course, you know that if one of the PN junction is reverse biased, there cannot be a lot of current flow in that particular reverse biased junction. So if you take into example of this scenario, that you have an this is an NPN BJT. So the symbol of an NPN BJT looks like this. So this is the symbol of a BJT. And again, for a BJT, the direction of the arrow will be very similar to the direction of the MOSFET. Remember that for NMOS transistor, the way we represented NMOS transistor is this, that this is the source, this is the drain, and this is the gate. For an NPN BJT, which is analogous to your NMOS transistor, this will be your emitter, and you'll have your direction of the arrow over here. So it's very similar to your NMOS transistor. So this is your emitter terminal. This is called the collector or the drain terminal. So collector, drain, sink, these are all different names of the same thing. Similarly, emitter and source, it's doing the same job, as you can understand, that it either emits the charge carrier, or in this case, it's the source of the charge carrier. So it's doing the same job. The only difference for a BJT, or perhaps the most biggest difference for a BJT, is that for the base terminal, which is equivalent to the gate terminal of the NMOS transistor, and the gate terminal or the base terminal is basically the control terminal. That's why you have the control over the device, and that control over the device is established using a gate voltage for an NMOS transistor. In this case, that control will be established through a base current for the BJT. So the BJT is a current controlled current source. So this current at the base will determine how much current will flow at the collector. For the MOS transistors, the gate to source voltage determines how much current that will flow through the transistor. So this is a voltage controlled current source. This is CS, whereas a BJT is a current controlled current source. So CCCS. But then apart from that, everything else will be very similar for your BJT versus the MOS device. Now, the most important equation that you'll see for a BJT is that the collector current, IC. So IC is called the collector current, just like the drain current for a MOSFET. So collector and drain, they are the equivalent terminals for the BJT versus the MOSFET. Now, the most important equation that you have is the collector current, which will be very, very similar to the emitter current, almost equal to the emitter current as well. So that collector current will be equal to beta times IB. So beta is the amplification factor in the current, or the amount of current gain that you have in the device. Beta times IB, that's the base current that is going into the base terminal of the BJT. Again, that's the biggest difference, that there could be current flow, or there is a current flow at the base terminal of the BJT, but there is no current flow into the gate terminal of a MOSFET. So for this BJT, and this is an NPN type BJT, right? So this is N, this is P, and this is again N. Okay. So remember, in this case, what is happening is that you are trying to push in a current at the base terminal. From the collector to the emitter terminal, there is also another current flow. And the current flow, the amount of current that flows through the collector terminal is beta times IB. So that's the governing equation for your BJT. For your MOSFET, the governing equation was the drain current is GM times VGS. In this case, it's beta times IB. But that's possibly the biggest difference that you'll see in the MOSFET versus the BJT. But as you see that the circuit looks very similar, that you have a voltage that is applied between the base to emitter terminal. You have a voltage that is applied between the collector and emitter terminal, just like you apply a VDS and a VGS for the MOSFET. Okay. So the analogy between the MOSFET and BJT is provided over here in terms of all the equations and what should be the expected GM, what should be the expected RO, and so on. So all these things are provided over here. Please go over them, and please go over the pre-recorded lectures that I have posted on Canvas. So they are from 2022, last year, but you'll see that whatever you have studied till now will fit in very well with the concepts for BJT as well. All right. So something I wanted to discuss or start today was CMOS logic-based circuits, because this is your lab 7, and your lab 7 is due this week. So I wanted to start with your lab 7 topics. Those are the CMOS logic circuits, and I wanted to put the BJT discussions as a self-study. So for MOS logic, what do we actually mean by MOS logics or CMOS logics? So till now, whatever we have discussed are analog circuits. You have a continuous voltage or current, and you are analyzing those continuous voltages and currents at the input or output of a circuit. The biggest difference with digital logic with analog logic is that, or analog circuit is that, maybe I can write that down. So basically digital is, analog is continuous time, continuous signal. So if you're continuous in time domain, and if your signal is continuous, then you call it analog. That, let's say you are looking at a sine wave. So the sine wave, so this x-axis is the time. So your time axis is continuous, and the signal that you are looking at is also continuous. Okay. Now you can look at discretized time instants. So let's say this is 0 seconds and this is 10 seconds. So you have a sine wave that has that starts from this 0 second, goes to peak, comes back again at the initial level. So let's say that it does at 5 second time, and then you have the negative half cycle that goes from 5 seconds to 10 seconds. So over this entire 10-second time duration, you have the full sine wave. Now, if you sample each second, that every second I want to find out what is the value of my sine wave. So your first sample would be somewhere over here. The second sample will be at 1 second. And by sample, I really mean what you mean by samples in traditional English, that you're just taking samples of the signal at every second. You're taking the value of the signal at every second. So that's what is meant by sampling, that you sample the value of the signal at certain points, certain discretized points. So even though your original signal was continuous time and continuous signal, if you take samples out of it, what would happen is that your time will not be continuous anymore. So time will be discrete. So if you take samples, you'll be discrete time, but still you'll be having a continuous signal. Why I'm saying that you'll have a continuous signal? That's because the value of the sine wave does not become quantized. So the sine wave follows some analog pattern. So it's not that the values are 1, 2, 3, 4, 5, and then again coming back to 4, 3, 2, 1, and 0. So it's not same as quantizing in time domain. So in time domain, as you're quantizing, you are taking these discrete values, 1, 2, 3, 4, like this. But the value of the signal is not discrete. It may be 1.304. It may be 5.67219, and then ... You just have more and more numbers to represent the actual value of the signal. So the signal is still in continuous domain. So that is called discrete time and continuous signal if you have sampled a sine wave. But now let's say you have also sampled and quantized the value of the signal as well. So in that case, it's called quantization. And the way a quantized sine wave looks like is that if this was your original sine wave, If this was your original sine wave, and let's say at certain points you're quantizing. So at 0, your value is this much. At 1, let's say your value is this much. At 2, your value is this much, and so on. So if you sample and quantize, your signal may look something like this after doing the quantization and sampling. So instead of a clean sine wave, you'll see these steps going up. So these steps are going up, and then steps coming down. Again, there are steps that are coming down, and then again steps that are going up. So if you discretize both in time domain as well as in terms of the value of the signal, so if you discretize them with certain values, let's say your time is also 0 second, 1 second, 2 second, 3 second, like that. And in your signal domain, you have this as 0 volts. This is 1 volt. This is 2 volt. This is again 1 volt, 0 volt. This is minus 1 volt, minus 2 volts, and so on. So if both your time and signal values are quantized, then it is called discrete time and discrete signal. And that discrete time, discrete signal logic is called a digital logic. So that's the difference between analog and digital. So analog means you have continuous time, continuous signal. If you just sample in time domain, that's not enough to call it digital. When you are calling something digital, then it really is discrete time and discrete signal. And many of the times, your discrete signal values will have only 2 values. So that's called binary digital logic, where your discrete signals are either 0 and 1. So it can be represented with 0 volt and 1 volt, or 0 volt or 5 volts. But basically what you're saying is that you have 2 digital logic levels. One logic level is logic 0, the other logic level is logic 1. So we'll learn about some of these digital logics using MOSFETs or BJTs. So we'll mostly focus on MOSFETs here. So we'll try to see that what kind of CMOS-based circuits we can build for digital logics as well. So till now, whatever we have discussed was for analog, continuous time and continuous signal, but we'll also learn a little bit about digital in the next 3 lectures or so. But these, the discussions on CMOS digital logic will not be part of your final exam, will not be part of the exam on Monday. You'll of course have the homework number 9 though, which will be based on your CMOS logic circuits. Yeah, because if you're learning something, we'll like to know that how much you have learned through a homework problem. But it will not be part of your final exam, just to reduce some workload from the final exam syllabus. Okay. All right. So how do the way I would like to start the discussions on MOS logic is that you already know about, let's say, these kind of circuits, that you have an NMOS transistor over here, you have a resistive load, okay, and then you are applying your input to the gate. So basically that's a common source type configuration, that you have your input at the gate, your output is at the drain, and at the source terminal you are grounded. Now, if you draw the operating curves of this particular circuit, let's say you just want to have the ID versus VDS characteristic. Okay, so ID versus VDS characteristics, and let's call that VDS, the V drain to source, which is this voltage, as your output voltage, because the output voltage is also taken at the drain terminal, but your source terminal is grounded. So VDS is equal to your V out. You know that the ID versus VDS characteristics look something like this for the transistor, that it will have an active region or saturation region, which is basically the right-hand side of this curve. So whatever you see on the right-hand side, where the current saturated, is your saturation region or your active region. On the other hand, we could draw a load line for the load resistor as well. So this load line is the line that is connecting VDD over RL, this point. So VDD over RL is the point when, if you assume that this transistor is on, and it is on in such a way that you can consider this transistor as a short, that it offers no effective resistance at all. Let's say at this point, looking down, if your transistor is in saturation, you know that it offers a resistance of RO, right? When you're looking at the gain of the transistor, which is in saturation. But there are other regions. For example, there is the linear region, when the resistance of the transistor can be very, very low. If that resistance is almost zero, if that resistance looking down is almost zero, what is the current that flows through this path? If this resistance is zero, then the only resistance that you have between VDD and ground is this RL resistance. So this point, VDD over RL, gives you the value of that current when this transistor can be regarded almost as a short. So at that point, you're deep in the triode region. So this left-hand side region is the triode region, right? So at that point, you're deep in the triode region for the transistor. So the VDS, the drain to source voltage drop of the transistor is almost zero. So you're effectively around this point, that the drain to source drop is almost zero. So your x-axis value is almost zero over here, right? So let's just consider this small region over here. So the x-axis value is almost zero. The drain to source drop is almost zero, which means that the current through the system is determined by this VDD over RL. So that's this point. On the other hand, there is another point over here when the current is equal to zero. So the drain to source drop is equal to VDD. If the current through this path is equal to zero, then the drain to source drop is equal to VDD, and that is the point which indicates that this transistor is an open. So in analog circuits, we are considering the transistor as the behavior of the transistor also as a continuous function, right? We were thinking about how the current through the device changes as you are changing the VGS, as you are changing the VDS, as different parameters of the transistor changes, and so on. In digital logic, all you care about is whether the transistor is on or the transistor is off, which means whether the transistor acts like a short or does it act like an open. When the transistor is off, it acts like an open. When the transistor is on, it will act like a short. So that's what digital logic will tell you. So if you are just interested in the logic, but at the end of the day, the device is an analog device. It's a continuous device. So of course, you need to consider certain parts or regions of this ID versus VDS characteristic that will be analogous to your assumption that the device could be either on or off. So of course, off means the current through the entire system will be zero. So this is the line where that will be analogous to the device being off, that the entire voltage drop will be happening across the device. On the other hand, if the device acts as a short, then the current flow through the entire system will just be equal to VDD over RL. So that's the point you're interested in. So those are the 2 points you will be interested in, or around that point you'll be interested in when you are talking about digital logic. But what is interesting in this curve is that you can figure out, or you can design or you can even predict your VTC, the voltage transfer characteristic of the device, just from the load line and the ID/VDS characteristic of the device. How you do that? Remember that when we try to find out the VTC of a device, what we are really plotting is the V out versus V in. So in this case, your x-axis is your V in, your y-axis is your V out. So when your V in is very low, when the gate voltage of this transistor is very, very low, of course, you'll expect that the VGS is very low, or it's almost equal to zero. So if VGS is almost equal to zero, at that point, the device works as an open. So the device is off. Your VGS is zero. Your VGS is much lower than VT. So the device is off. And if the device is off, what is the output voltage according to these curves that you see on the top? So if the device is off, the entire voltage drop will be happening across the device, because the device is off. The entire voltage drop is happening across the device. So your output voltage, V out, will be equal to VDD. That's when the device is off. So your output voltage is equal to VDD when your input is lower than a threshold voltage. That means when the device is off, your output voltage is equal to VDD. And when the device is on, the device is fully on, that is in this region, when the drop across the device, so the meaning of the device being on is that the drop across the device is almost equal to zero, which means that the device is a short. If the drop across the resistance is almost equal to zero, you say that the resistance basically acts like a short, right? It does not act like a resistance. So same thing over here, that if the drop across the device is almost equal to 0, the device acts like a short, which means that the VDS of the device is very small. It is almost equal to 0. So that means that you are in this region. So if you are in deep triode, then you say that the device is on. And at that point, the VDS of the device is almost equal to 0. And in between, you have all these points, which are basically this point, that point, this one, and so on. So in between, you have all these points that the device will go through as it goes from the cutoff region or the off region to the on region or the triode region, right? So in digital logic, you are interested in the cutoff region when the device is off and the triode region when the design is on. On the other hand, for analog circuit design, you're only interested in the saturation region, which is over here. So in the VTC curve, this is the way you should understand the difference between analog and digital. Digital is whatever is drawn in blue. Analog is whatever is drawn in red. So if you are interested in the analog property of the device, you should be interested in this region in your VTC. If you're interested in the digital properties, you should be interested in the left and right hand side of the device. So we'll stop here. We'll start discussing about digital logic in more detail on Wednesday's lecture. Thanks, everyone.